Thank you. It's a pleasure to be here. So let me begin. So let R be a commutative Noetherian ring. I is an ideal in R. And M is an R module. So the check complex of M with respect to the F's is the following. So it's 0, M, the direct sum of M sub Fi, direct sum over all I, of course, a direct sum over all I smaller than J, M sub Fi of J, and so on, M sub F1 Fs to 0, right? And the local cohomology module, so the ith local cohomology module of M with support in I is the ith cohomology module of the check complex. All right, so you may consider this a definition, although the definition, in fact, is different. This is a theorem, but for the purposes of the talk, this is the definition. Local cohomology modules are usually huge. They are not finitely generated as a rule, and so on. So, however, one still can ask whether they have some finiteness properties. So the question that I will be dealing with today is the following. Assume M is finitely generated. So M is a finitely generated R module. Is the set of the associated primes of the local cohomology module of M finite? All right, so we know that the set of associated primes of a finitely generated module is finite. So local cohomology modules, as I said, are not finitely generated as a rule. So if they had finitely many associated primes, that would be a significant restriction on the structure of local cohomology modules. Here is some of what is known about the question. So answers. So not necessarily. The first counterexample was produced by Anurag Singh, and it was an example of a hypersurface R over the integers, so that certain local cohomology module of R with support in some ideal has p torsion for every prime p. So for every prime integer. Later on, Mordechai Katzmann produced an example so it's a local ring essentially of a finite type over a field. And a suitable local cohomology module has infinitely many associated primes. So these are negative results. Now, what about the positive results? One should modify the question and ask, is the answer positive if R is regular and if the module M is R, right? R itself. So this has a considerably better chance of having a positive answer. So here is some evidence that the question probably has a positive answer. So answers. So yes, if R contains a field of characteristic P. So this is due to Craig Hunicke and Rodney Sharp. Also yes, if R is finitely generated over a field of characteristic 0. And so yes, if R is a complete local equicharacteristic 0. And also, if R is unramified complete local mixed characteristic. So these are all proven by me. And very recently, so very recently, it's number 5. A result due to Bargov-Butt, Manuel Blickley, myself, Anurag Singh, Wenliang Zheng. So yes, if R is a smooth Z algebra. So for instance, R is the ring of polynomials over Z, infinitely many variables. Okay? So these are some of the positive results in this direction, but in the general case, the question is still open. So the key open cases are the following. R, non-local, contains a field of characteristic 0, and secondly, R is ramified, complete local, of mixed characteristic. All right? Well, we need in the theorem we need that the condition that R modulo every prime is a regular ring, and I think this is the smoothness property. Regularity is not enough. Regularity is not enough. We don't have a proof simply assuming that it's a regular Z algebra. That's still open, yes. But that is included in here, because if there is a prime for which I maybe not. Well, closely related at least to this. Okay, so today I'd like to give some idea about the proof of this result, and also to a degree review the methods that are involved in proving all the other results. So the basic method is D modules. Sketch of proofs. So assume that R is some other ring R prime adjoint finitely many variables, right? So let me denote by D, which is D of R prime. So the ring of R prime linear differential operators of R. So what is this? It's a sub-ring of the R prime linear endomorphisms of R. And it contains containing R prime. So R prime sits inside D, and also the following differential operator. So 1 over T prime, partial differentiation of order T with respect to, so T factorial, I mean, with respect to xi. So that's an R prime linear map of R into R. And so this also sits inside D. Right? So and then the ring of differential operators is the smallest subring of the endomorphisms that contains R prime and all these. Right? So the key facts that are going to be used in the proofs are the following. First, if P is any element in R prime over here, so P is in here, so then the ring of D modulo PD is exactly the ring of R modulo the ring of R prime modulo PR prime, so linear differential operators of R modulo PR. Right? So you mod out by an element in R prime, and you get exactly what you expect. The ring of the differential operators of the new ring that are linear with respect to the new coefficient ring. Secondly, before I state the second fact, you know what? Let me erase this for the time being, just a second. So D is not a commutative ring, so a D module is a left D module. So for example, R is a D module. All right? So with the usual D action on the left, every element of D acts on the left. R prime acts via the multiplication by elements of R prime, and R acts via multiplication by elements of R, and all these differential operators through differentiation. So now, the key facts. If P is in R prime, so D modulo PD is the differential operators of R modulo PR, linear with respect to R prime modulo PR prime. Secondly, if F is an element in R and M a D module, so then M sub F is a D module. So there is a natural D module structure on M sub F. How so? Well, you just differentiate a quotient. And this is a rule from calculus, which we can extend formally to this algebraic situation. So via the quotient rule, you extend the action of each of differential operators to M sub F. All right? So as a consequence, as a consequence, the check complex is a complex in the category of D modules. And as a consequence of this, local cohomology module of R with support in I is a D module. All right? So, and a very important fact is the following. If R prime is a field, so then, sorry, that's of M, is a field, so then R sub F has finite length in the category of D modules. So that's a very important property, because R sub F certainly has infinite length in the category of R modules. But in the category of D modules, the length is finite. And the consequence of this, finally, is that so everything in there, in the complex, has finite length. So so the check complex, you know what, let me of R with respect to F1 through Fs consists of modules of finite length. All right? And therefore, so therefore, continuation of 3, hi sub I of R has finite length in the category of D modules. Right? So that's a crucial fact for the case in which R prime is a field. All right. And now let me show you how this implies that all these local cohomology modules in the case in which R prime is a field have finitely many associated primes. So theorem. So let R be K adjoint x1 through xn. Local cohomology modules of R with support in I have finitely many associated primes. Well, so how do you prove this? So we are going to prove that. So here's a proof. So we are going to prove a more general statement. If M is a D module of finite length, so then M has finitely many associated primes. So why so? So that's a claim, all right? And so here's a proof. You take a maximal filtration of M in the category of D modules. So it's a maximal filtration in the category of D modules, and then a standard fact says that the associated primes of M is a subset of the union overall I of the associated primes of M I modulo Mi minus 1. All right? And each of these over here is a simple D module. So, and another claim is that if M is a simple D module, if M is a simple D module, so then it has a unique associated prime. All right. So each of these is simple. It's a simple D module. There are finitely many of them. And therefore, the set of the associated primes of a module M is finite, because it's contained in the union of all these. So how do you prove the claim? So let P be a maximal, so be maximal in the set of the associated primes of M. So then, if you take the zeroth local cohomology module of M with supported P, so first of all, this is M is a D module. So any local cohomology module of a D module is a D module. So this is a D module, and it's a proper submodule of M. It's a proper submodule of M since P is a maximal associated prime. And so we assume that it's not unique, right? So therefore, it's a proper submodule, and it's not equal to 0. All right? So non-zero, not equal to M, therefore, it contradicts the assumption that M is simple. So I should say that assume, so let P be a maximal in the set of associated primes of M, and assume it's not unique, right? And assume it's not unique. So then, this is not M, and it's not equal to 0. So if P is maximal and not unique. All right, so that's a proof. So as you can see, using the key facts that I pointed out over there, actually the fact is over here, right? One immediately gets that the set of associated primes of local cohomology modules, in the case in which our prime is a field, is finite. So what about the new result that we proved very recently, about half a year ago? That's the main topic of the talk. So now let's assume, so for the rest of the talk, no. So now, R is the integers adjoint a few variables. So I will only prove the statement in this special case. So the polynomial ring over the integers, all right? And so we consider certain local cohomology modules. So you take any ideal in R and consider the local cohomology module. And so let P be an associated prime of hi sub I of R. So there are only two possibilities. Either R intersect, sorry, P intersect Z is 0, or P intersect Z is a prime ideal, a non-zero prime ideal. So generated by a prime integer P. Right? So, well, first, we are going to show that the associated primes of the first type are finite in number. Claim the set of primes P of type 1 are finite. Maybe I should say the number of primes of type 1 is finite. So why so? So well, here's a proof. P is of type 1 if it survives in R, a tensor with the rationals over Z. And that's the ring of polynomials over a field. Right? So that's the ring of polynomials over a field. And over a field, we already know that the set is finite. Right? Over a field, so we already know that the set of the associated primes is finite. So that's the proof. The set of the prime ideals of the first kind is finite. All right, so what about the second claim? For a fixed prime integer P, the set of the associated primes, capital P, of type 2 is finite. Right? So for a fixed prime integer P. All right? So, all right, here is a proof. So if you take the short exact sequence, here you multiply by P. And this, of course, produces a long exact sequence. So here you'll have h I minus 1 sub I of R modulo PR. Then here you'll have hi sub I of R. So multiplication by P, h I sub I mod of R. Right? Okay, so let's see. So this is a short exact sequence in the category of D modules. So this is a sequence in the category of D of R Z modules. Right? So Z linear D modules of R. All right? So therefore, this is also a sequence in the category of Z linear D modules of R. And now, this is a D module that is annihilated by P. It's a D module that is annihilated by P. So H I minus 1 sub I of R modulo PR is a D module which is annihilated by P. Therefore, this is a D modulo PD module. All right? So because it's annihilated by P. Now we go back to what I stated before. Nope. Key fact 1, D modulo PD is the ring of differential operators of R modulo PR that are Z modulo PZ linear. Right? It's a key fact 1. Now, what is this? This is a ring of polynomials over a field. So that's Z modulo PZ adjoint the same x1 through xn. Right? So this is a field. So Z modulo PZ is a field. And therefore, the module, the local cohomology module, has finite length over this ring. Over this ring. Right? So now you take the image of this map. The image of this map in here. All right? It's a quotient of this thing in the category of D modules. Therefore, since this has finite length in the category of D modules, the image of this map in here also has finite length in the category of D modules. And I have already pointed out that if it has finite length, then the set of the associated primes is finite. So the set of the associated primes of the module hi sub I of R that contain the integer p are also the set of the associated primes of the kernel of the multiplication of this module by p. All right? And that is a D modulo PD module that has finite length. All right? And therefore, the set of the associated primes is finite. So this finishes the claim that for a fixed integer p, the set of the associated primes of the local cohomology module that contain this integer p is finite. Now, so what else is there to prove? Now we need to show that nope. What did they do? So now all that remains to show is the following. h I sub I of r has p torsion for only finitely many prime integers p. Right? That's all. So then we'll have finitely many prime integers p for each one of those, the set of the associated primes that contain that integer is finite, and we will be done. Okay. So here's a proof of this. Well, you take a look at the Kazul, at the Czech complex. Did I? Oh no, here it is, right? So, and in it, you consider the set of all the fractions in which the denominator has power 1. All the f's in the denominator have power 1. So 0, this is the Kazul complex of R. So in our case, it's R. So 0, R, a direct sum of R over Fi, a direct sum of R over Phi J, and so on. And here you have the Czech complex. And so on. So what did I take over here? I took all the fractions in which the powers of f's in the denominators are equal to 1. Right? And that's a subcomplex of the original Czech complex. And this, of course, there is a map. So here it's the identity map, and over here it's the inclusion. Right? And this induces a map from the Kazul homology. Kazul homology to a local cohomology. Right? So here you have a map of complexes, and that a chain map, and that induces a map on the cohomology level from the cohomology of the Kazul complex to the cohomology of the Czech complex. And a crucial fact that I did not include in the list is the following. So this, of course, is true for any R. For any R and any F's. So the crucial fact is the following. And it was proven a few years ago by Josep Alvarez, myself, Manuel Blickley, and myself. So it says the following. If R is K, a joint x1 through xn, and K is a field of a characteristic P, so then the image of the Cazul cohomology of Hi. That's Hi of K of R F1 and so on. So the image of Cazul cohomology in the local cohomology generates the local cohomology module as a D module. All right? It certainly cannot generate the local cohomology module as an R module because the image of the Cazul homology module is finitely generated as an R module. So if you take a submodule of any module that is generated by a finitely generated R module, you'll get a finitely generated R module. And local cohomology modules are, as a rule, not finitely generated. So as an R module, it certainly cannot generate the entire local cohomology module. However, as a D module, it does. And the assumption that the characteristic is P is a very important assumption because in characteristic 0, this statement is false. So we know that it's false in characteristic 0. It's a special property in a characteristic P. Now, all right, with this, we can finish the proof in the following way. No. So again, you have the usual short exact sequence, so multiplication by P. This induces short exact sequences on Cazul complex and the Czech complex. So we'll have the following long exact sequences. Just a minute. So Hi of K of R. So that's the Cazul homology. Here you multiply by P. Hi K R, then Hi plus 1 K no, that's not what I meant. So okay, let's see. K R multiplication by P Hi K R Hi K R modulo P R Hi plus 1 K R, here Hi plus 1 K R. So here it's also multiplication by P, and over here you have a similar thing for local cohomology modules. So I sub I of R, H I sub I of R, H I of R modulo PR sub I, and HI plus 1 of R multiplication by PH I plus 1 R I of R. All right? So now let's assume that that the multiplication by P, so here you have the usual maps from the Cazul cohomology into local cohomology. So let's assume that multiplication by P on the Cazul cohomology modules is an injection, right? Let's assume that, so here, assume it's injective. All right? So this is injective. The multiplication by P. Now, this implies that over here the kernel is equal to 0. So here, this is onto. All right? So it's injective. So we assume it's injective. Therefore, the kernel is 0. Therefore, the map over here is onto. All right? Now, you take the composition of this map with the map over here. It's the same as the composition of the map downward and the map over here. All right? Now, what I mentioned before is that the image of this map in here generates this module as a D module, since this is in characteristic P. And this is a sequence in the category of D modules. Therefore, so what do we know? We know that the image of this in here is in the image of this in here, since it comes from a common source. All right? So we know that the image of this module in here contains the generating set of this in the category of D modules. Therefore, the image over here is, the map over here is a surjection. All right? Is a surjection, and therefore, so it's a surjection, and therefore, this is, so it's a surjection, so therefore, over here, it's an injection. All right? So the conclusion is the following. If the multiplication by a prime integer on the Cazul cohomology module is injective, then it's injective on the module itself, on the local cohomology module. Well, now we are done, because the Cazul cohomology module is finitely generated. So there are only finitely many prime integers on which the map is not injective. And on all but finitely many, the map is injective. So you take those all but finitely many prime integers for which the map is injective on the Cazul cohomology module, and the conclusion is that the multiplication by all those is injective on the local cohomology module. Therefore, the set of the prime integers such that a local cohomology module has a p torsion is finite. So this completes the proof. Now, before I finish, I would also like to point out that to mention another open problem for any ring, not only regular. So here is a completely open question. Well, not quite completely, but almost completely. So here is a question. Let R be any commutative Noetherian ring. is the set and M a finitely generated R module? Is the set of the minimal primes of a local cohomology module of M finite? Right? So not associated, but minimal. There are no counterexamples. The counterexamples that I mentioned before, the infinitely many associated primes are all embedded. They're not minimal. But that's almost completely open. All right, that's all.